But let's move on to 311. On hyperbolic functions, or sometimes called hyperbolic trig functions. So these hyperbolic functions are named fairly similar to the trig functions. So we have a trig function like sine x. We have a hyperbolic function sin h of x. This is usually pronounced sinh of x, like almost like if you were to say sinh a drawstring or something like that. So sinh of x, the hyperbolic sine, function. And it's defined as sinh of x equals e to the x minus e to the negative x over 2. We have another function, the hyperbolic cosine of x, cosh of x, is e to the x plus e to the negative x over 2. And we might already see a little bit of relationship with the regular trig functions. We note that sinh of x is odd. In other words, sinh of negative x equals negative sinh of x, and cosh of x is even. Cosh of negative x equals cosh of x. So they have these nice symmetry properties. We also see that they're pretty clearly related to one another. And we'll investigate that a little bit more later on. From these two, we can build up other hyperbolic functions. For instance, tanh of x, the hyperbolic tangent of x, sinh of x over cosh of x, or we can see from the definition that that is e to the x minus e to the negative x over e to the x plus e to the negative x. And we have the others, hyperbolic cotangent of x, hyperbolic secant of x, and hyperbolic cosecant of x, which I've never heard called anything other than just how I said them, similarly defined. Right. The hyperbolic cotangent is 1 over the hyperbolic tangent. The hyperbolic secant is 1 over the hyperbolic cosine, and the hyperbolic cosecant is 1 over the hyperbolic sine. So where do these come from? So sine and cosine are intimately related to the unit circle, right? The bane of everybody's existence in trig. So a point on the unit circle relative to an angle theta is cos theta comma sine theta. Well, what if I considered something related to, instead of the unit circle, if I considered what maybe we could call like a unit hyperbola? So what if I looked at x squared minus y squared equals 1 instead of x squared plus y squared equals 1? So I see that when y is 0, I get x squared equals 1, I get solutions. When x is 0, I get negative y squared equals 1, I get no real solutions. So that tells me the hyperbola is opening left and right. I have a point here that is at 1 comma 0, and a point here that's at negative 1 comma 0. And I kind of traverse these hyperbolic legs over here or whatever as I change my values of x, my inputs to the hyperbolic trig functions. So a point on this curve is cosh of x comma sinh of x for some kind of understanding of x. I shouldn't call it x. I was just using an arbitrary input there, but I've already used x. I should use something like t or something like that. We can use t or something like that. Some variable doesn't, but this point on here is related to the idea of hyperbolic cosine comma hyperbolic sine. So we can see that they're related in the sense of maybe the symmetry up here, but we can also see that there's a deeper geometric relationship without having talked about parametric equations, which is more of a Calc 2 topic. It's a little hard to go into much more detail in the background here, but the one thing that we might notice is that it seems like we have a pseudo-Pythagorean relationship, right? This, along with this idea, gives us the Pythagorean identity. Well, it seems like we should have a pseudo-Pythagorean identity. In other words, it seems like cosh squared of x minus sinh squared of x should equal 1 if this relationship up here is true. So let's check that. What is cosh squared? Trying to get both of them on here, but I don't think it's going to. But cosh squared is that. And sinh squared is that. I get a 1/4 out of everything. And then what do I have? I have e to the 2x plus 2 e to the x e to the minus x. That's just plus 2 plus e to the minus 2x. That's from the cosh squared numerator. And then minus from the sinh squared numerator, I get an e to the 2x. And then I get minus 2 times e to the x times e to the minus x, which is just minus 2. The e to the x times e to the minus x cancel. And then I get plus e to the minus 2x. E to the 2x and e to the minus, or e to the 2x minus e to the 2x go away. E to the minus 2x minus e to the minus 2x goes away. I get 2 minus negative 2, 2 plus 2 is 4. Over 4 is 1. So I have a nice identity here. I sometimes refer to it as the pseudo Pythagorean identity. It's the analog of the Pythagorean identity in this equivalent idea over here of using a hyperbola instead of a circle. Right. So why would we expect this to be true? It's because these hyperbolic functions are defined based on hyperbolas, and hyperbolas are differences of squares and not sums of squares. I mentioned up here that sinh is odd and cosh is even, which we can pretty readily see from the definition. Tanh is, of course, odd. And we also have sum of two angles formulas, which I'll write here. I don't think there's really any reason to memorize them, but just to show you them. Sinh of x plus y is sinh of x cosh of y plus cosh of x sinh of y. This looks fairly similar to sine of x plus y. And cosh of x plus y is cosh x cosh y plus sinh x sinh y. Again, looks pretty similar to the cosine of the sum of two angles. And that's kind of the story with a lot of these hyperbolic functions related to trig functions, is the identities and things look very similar, but sometimes they're just like off by a negative. And I don't know if that's good or bad, right? In some sense, looking pretty similar means that you kind of say, okay, if I know something about the trig functions, I can probably make an educated guess about the hyperbolic functions, but sometimes being off by only a little bit means that it's really easy to make a mistake or forget which idea goes with which one. Okay, so what are their derivatives? Now, nicely enough, if I had to work directly from this hyperbola, it would be a real headache, right? The same way that when we first defined what's the derivative of sine of theta with respect to theta, that was kind of a headache, right? We had to go through a big geometric argument to get to the derivative of sine of theta. But nicely enough, my hyperbolic functions, I can write them in terms of exponential functions, and I know how to differentiate exponential functions. So what's the derivative of sinh of x? Well, this is clearly the 1/2 comes out, the e to the x differentiates to e to the x, e to the minus x differentiates to negative e to the negative x. So I get a plus e to the negative x. This is cosh of x. And what's the derivative of cosh of x? Well, the 1/2 comes out. E to the x differentiates to e to the x, and then we get a minus coming down. Well, that's sinh of x. So these cycle every 2 instead of every 4, like the regular trig functions, right? Derivative of cosine was negative sine, but here derivative of cosh is just regular sinh. So sinh second derivative is itself, where sine's fourth derivative is itself. What's the derivative of tangent of x, the hyperbolic tangent? Well, I can look at this and say, okay, that's the derivative of sinh over cosh of x. Or this is with the quotient rule, some stuff over the bottom squared. And on the top, I have bottom derivative of top. So bottom is cosh of x, derivative of sinh of x is cosh of x, minus top sinh of x. Derivative of bottom, derivative of cosh of x is just regular sinh of x. So that's cosh squared minus sinh squared over cosh squared. But remember our pseudo Pythagorean identity was cos squared minus sin squared is 1. So it's kind of like eerily similar to doing trig functions, right? It's like being in a slightly alternate universe or something. And we would call this the hyperbolic secant squared of x. So the derivative of hyperbolic tangent is hyperbolic secant squared. So if we think back to regular trig functions, say sine and cosine, the inverse functions aren't really easy to deal with. Arc sine or arc cos. I don't really have a good way to deal with those other than just kind of trying to move back into the regular sine and cosine and work something out, you know, kind of like we did with, say, implicit differentiation, that kind of idea. What about the sinh and cosh functions? Well, because I have sinh and cosh defined in terms of exponentials, I actually have a pretty decent chance of being able to invert them, right? I have an algebraic relationship with a function that I know how it works. And we won't go through the details, but we do have inverses that can be written explicitly. So the arc sinh of x, the inverse sinh of x is, and I mean explicitly in terms of some other inverse function, so maybe it's not quite as satisfying as it could be, but it's the natural log of x plus square root of x squared plus 1. And this is for all real numbers x. The arc cosh is log of x plus root x squared minus 1. And this is for values of x bigger than or equal to 1. And the arc tanh 1/2 log of 1 plus x over 1 minus x. And what are the derivatives of these? Well, let's do one derivative and then I'll leave the other two as exercises. So hopefully at this point, we're pretty good with the chain rule. So derivative of log of stuff is 1 over stuff. Times the derivative of that stuff. So d by dx of x is 1. And now I need to take the derivative of root x squared plus 1. Derivative of root of stuff is 1 over 2 root stuff. Let me give myself a little more room here. So derivative of the square root of stuff is 1 over 2 root stuff times the derivative of the stuff inside, which is going to give me a 2x. Those 2's will divide out. My OneNote is starting to act up again. I tried closing everything before class and all of that. And what can we do here? Maybe maybe we can try to get a common denominator in the numerator. So in the numerator, I need root x squared plus 1 over root x squared plus 1, and then plus x over root x squared plus 1. And I note that these are going to cancel now. So I get 1 over root 1 plus x squared. Kind of interesting, right? Derivative of arctan was 1 over 1 plus x squared. Derivative of arcsinch is 1 over root 1 plus x squared. And I'll leave these two as an exercise, but I'll write them out. Derivative of arc cosh. One over root x squared minus 1. And derivative of arctanch is 1 over 1 minus x squared. So again, pretty interesting, right? Derivative of arctangent is 1 over 1 plus x squared. Derivative of arctanch is 1 over 1 minus x squared. You can see why these are sometimes called the hyperbolic trig functions, because they have so many relationships to the trig functions. Okay. All right, I think we can get through this example in 10 minutes or so, and then we might go through another example or two when we come back. But let's consider a line hanging between two poles. So this cable has gravity pulling down on it everywhere between these two poles. The curve that this cable makes can be modeled by the second derivative of y equals rho g over t. Here, rho is the linear density of the cable, g is gravity, and T is tension in the cable at the lowest point, times square root of 1 plus dy dx squared. So we have a differential equation model here. And this comes from some things related to physics and so on. We have a differential equation model. This actually would be quite a difficult differential equation to solve. Even if we were in diffie-q, this would be a pretty challenging one. It turns out that there's a trick that you can use to solve this one, but that's certainly well beyond the scope of this course. But we want to show that the following function satisfies this differential equation. Y equals t over rho g, hyperbolic cosine rho g over tx. Solves the differential equation. So we get a hyperbolic trig function as the solution for this hanging curve here. Okay, so I want to find y prime and y double prime. So y prime, I have t over rho g. Derivative of cosh of stuff is regular sinh of stuff times the derivative of the stuff inside, rho g over t, and they go away. And then y double prime, derivative of sinh is cosh of rho g over tx. times the derivative of the stuff inside times rho g over t. And my question is the second derivative the same as all that stuff on the right? So let's start with the right-hand side. So I want rho g over t square root 1 plus y prime squared. So that's sinh squared of rho g over tx. And I want to eventually make this look like y double prime. Well, 1 plus sinh squared, that's reminiscent of a Pythagorean identity, right? If I had like square root of, 1 plus or minus or something sine squared, I'd be thinking, can I change that into just the cosine squared under the square root, and then do the square root of cosine squared as cosine? So I know that kind of an idea works with regular trig functions. Will it work with this hyperbolic trig function? So if I look at my pseudo-Pythagorean identity way up here, I see I have cos squared minus sinh squared is 1, which means that cos squared is 1 plus sinh squared. So I'm going to use that. So 1 plus sinh squared of stuff is cos squared of stuff. And square root and cos squared. And I note that rho g over t cos of rho g over tx is indeed exactly y double prime, which is the left-hand side. So I've shown that this function, t over rho g cos of rho g over tx, does satisfy that differential equation.